Welcome PCS members and our friends to our today's first of two seminars. We have a pleasure that our first speaker, Professor Seung-Hun Lee, is here with us in our seminar room. So it's going to be a hybrid seminar. The lucky few people will be able to watch it live in person, and the others, we are behind the screens. So I would like to ask our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Yeah, thanks, Dylan. But before that, there's a short announcement. I mean, there's still a few spots. Actually, up to 8 people can go into the discussion room. So we still have like 6 slots. So anyone interested to go back to the old school seminars or old style seminars is warmly welcome. So we still have time. So otherwise, yeah, let me start. So today we have with us Seung-Hun E from University of Virginia. He's going to talk about toward a spin jam theory, semi-classical and quantum. Is everything okay? Yeah, okay, so Seung-Hun E received his PhD at the Johns Hopkins University in '96 and then hold a number of positions at National Institute of Standards and Technology in Maryland, in Gettysburg, in Maryland. And since 2000, Since 2005, he's permanently at the University of Virginia, where he's now a Commonwealth Professor of Physics, and his interests are centered around experimental condensed matter physics using neutron and X scattering, with the focus on strongly correlated systems where for a variety of reasons like strong frustration and interactions, the natural simple long-range order is suppressed. And so he's interested in understanding this kind of systems. And so with this, let's start our seminar and welcome our speaker.
We cannot hear any sound, so please unmute the speaker. Hello? Yeah, online we cannot hear. Yes, we have some technical issues. For some reason, it seems the seminar started without us. Okay. Okay.
So, first, I'd like to thank Alexei for arranging my stay here, and also I'd like to thank Sergey for very kind generosity, especially for lending me his bike. That made my life much pleasant here. So this talk, oh no, something strange. So then I cannot move.
You can just press enter.
Enter.
And also.
But no, okay, done. All right. So this talk is all about energy landscape. without worrying about the microscopic origin, let's just say we have these three different kinds of energy landscape. One is this nice smooth cone with a smooth surface. Another two with a very rough surface, but one has a nearly flat bottom. Another one is this called rodic funnel type. So this is hierarchical and non-hierarchical, say. But then at very low temperatures, these two energy landscape, the complex energy landscape, will exhibit the slow relaxations. However, these two are different. So the question I want to ask is whether these two complex energy landscape will exhibit different relaxation process. And of course, as an experimentalist, I'm interested in how we can prove these two different energy landscape experimentally as well. And then after that, we'll discuss what kind of microscopic origin can generate these two different kinds of energy landscape. So these are the list of things that I want to discuss. But before going into details, let me show you the references and collaborators. This over several years. The experimental measurements and analysis were done by two students of mine, Anjana Samarakun, he graduated already, and Xiao Hu, he's about to graduate. And they did experiment with Takusato's group at Tokyo University. The Monte Carlo simulations were done by my student Tianran Chen, he already graduated, and Jiawei Chen, who is my colleague at the University of Virginia. And analytical theory work has been done by Israel Klish. In fact, he's a professional, semi-professional flamenco guitar player. So he sometimes performs in downtown shows. All right. So the first I'll describe experimental work. Before that, the initial motivation was the following. So let's say we have this smooth cone. Then try to find when we cool the system down, then what happens at low temperatures. To understand theoretically, or first what we do is first we found what is the global ground state. And then we expand the Hamiltonian around this ground state and then take a quadratic term that harmony was like simple harmonic approximations. Then that theoretical scheme explains elementary excitations, right? It works fine. But however, that theoretical approach fails if we have this macroscopic metastable states. Yeah. So first trying to find the global ground state and approximating around the global ground state is not enough. I mean, it may be useful, in my opinion. In fact, it's at the end of this seminar, I hope I can convince you that that approach, in fact, and finding a global ground state, in fact, is irrelevant. Yeah. And so what we are trying to do is, instead of finding global ground state, we're just trying to find the energy landscape. Yeah, just as some kind of parameter space. And by studying this characteristic of the energy landscape, we hope we can understand the low temperature dynamics. All right.
And I guess the naive approach of doing, let's say, quadratic perturbation around the global ground state, yeah, is even worse for the spin gem than the spin glass, right?
Oh, yeah, I think so. Yeah, exactly.
Because it's flatter, so I mean, quadratic perturbation will be even worse.
Exactly. So entropy, in fact, the very good questions. In fact, entropy of metastable state here is a more massive than the funnel type. In fact, the glassiness is actually everywhere. For instance, back in 1970s, this spin glass was very hot topic, touching this cable. So it's ordinary spin glass. The system is the following. So we have this non-magnetic metal. Then we dope magnetic impurities at very low concentrations. So interaction between these magnetic impurities are governed by this long-range RKKY interactions, and coupling constants varies as a function of distance. In fact, fluctuates from positive and negative, anti-ferro and ferro, very random. Yeah, because magnetic impurities are residing randomly. Yeah, and this random randomness, the magnetic interactions, in fact, produce, when you cool the system down, then produce very nice viscous, bulk susceptibility measurements. So this is a hallmark. Viscous, high bulk susceptibility is a hallmark of glassy state.
What does it tell you?
This one, in fact, this. So this is like a Curie thing, right? But then, so this is a zero. I'll explain a little more later. But this is a zero field cool. So what they do is you cool the system down without any field down to base temperature, and then crank up a little bit of magnetic field, very small. Then you increase the temperature while taking the data. So then you have this. So this, in fact, is you're going into, we have. So let me just show you. So if you have this kind of funnel type energy landscape, right? Then if you cool down, then it goes around here, and then you cool warm up this temperature, then you'll access this excited state. That's why it goes up here. But now, instead of zero field cool, if you do field cooling, then field cooled at base temperature, and then crank up, and instead of this, you stay here. So it's called, I'll show you a little later, but field cooled and zero field cooled hysteresis is the hallmark of glassy state. So this, what kind of state the system access go into the low temperature depends on external magnetic field and very sensitive.
Yeah, but still, I mean, this peak which you showed there is, let's say, taken at zero field, right?
Right.
And what you see is that the susceptibility becomes largest at some characteristic temperature and then falls down. So usually that would mark some kind of conditional phase condition or whatever.
That's right.
So what is happening here?
So that's a big issue in the ordinary spin glass, whether this transition is real, and sometimes don't believe, sometimes believe this is a true transition, and some people say, well, this is a, the true transition is zero temperature. This is only due to this relaxation. So, so this is a correlation builds up, and then here, because of correlations, I didn't touch anything. I did. Correlations, and this correlations is, let's say, the anti-ferromagnetic. They effectively. Then this is like a summing up the sort of frozen moments. If they are aligned anti-parallel style, then the signal will go down. Yeah, and when you crank up a little bit, then instead of these anti-parallel, they have maybe canted or whatever. Then ferromagnetic component will get enhanced. That's why it goes up. Yeah. So this glassiness, this glassiness, in fact, the concept of glassiness, in fact, was used to explain also protein folding phenomena. And this in the field of protein folding, one major problem was protein is made of many, the collection of many amino acid, right? And the chain of this amino acid, and when let it fold, then they fold into a only specific native folded states. And even though there are many other possible folding patterns, only the patterns, only the protein that has this native folding state, they survive and has this life functionality. Otherwise, they're dead. So why that's the case? And this Orlenis, in fact, he's from the spin glass community, the theorist. He proposed this rugged Fresnel type to explain this protein folding as well. All right. Now this glassiness, in fact, the freezing phenomena, glassiness, in fact, appeared in a very different system of fluctuating magnets, for instance. But there are various systems, for instance, manganese, moly, and all these pyrochlor systems, and holmium and dysprosium, and their Hamiltonians are very different. So manganese and holmium, their Hamiltonian has dominant antiferritic exchange interactions and have a weaker single ion anisotropy. On the other hand, this holmium and dysprosium sample, they are called spinites. They have a strong single anisotropy, and then has this weaker ferromagnetic change. But you can see here, they all show this hallmark of glassy behavior, zero field cooled and field cooled hysteresis here. Another system, in fact, so this one has this anisotropy term. Another the system that was very hot back in 1990s, in fact, when I was a student. This was my thesis project. This one is called SCGO. The magnetic ions are chromium 3+ ions, and the magnetic ions form, I call it bipyramid lattice. Basically, when you have a pyrochlor lattice, 3-dimensional pyrochlor lattice, when you view this pyrochlor lattice along 1-1-1 direction, then you can consider that as triangular lattice, Kagome lattice, triangular lattice, and this is continuously appearing. So we can take the Kagome lattice, triangular lattice, and another Kagome lattice, and that's it. We can have these 3 layers. Then we will have this magnetic lattice by pyramids. I call it by pyramid because these are one tetrahedron and another tetrahedron sharing one corner. So I call it bipyramid. If you look at the one each bipyramid, then they form a triangular lattice, super lattice. Okay, and as you can see here, and now going to the physical chemistry, the chromium 3+ ion has 3 electrons in 2 levels, and so the neighboring chromium ions, each chromium ion is surrounded by 6 oxygens octahedrally, and neighboring chromium ions shall face 3 oxygens. So direct exchange interaction between these neighboring T2G electrons dominates the interactions. So basically, the false approximation, in fact, spin Hamiltonian is the antiferritic near-zero interaction only. And the further near-zero interactions are negligible. And there's no single anisotropy term because chromium 3+ ions has quenched the angular momentum. All right. So it's in fact, it realizes experimentally very nice simplistic spin Hamiltonian and frustrated spin Hamiltonian. And J is very strong. The Curie temperature is about 500 Kelvin. But it does not order, when you cool the system, it does not order down to about 5 Kelvin. Yeah, so from 500 Kelvin down to 5 Kelvin is a classical spin liquid. But then 5 Kelvin, it undergoes some kind of freezing, as Sergey mentioned. This is spin freezing. When you do neutron scattering measure, elastic neutron scattering measurements, then you see this order parameter behavior below 5 Kelvin. And you can see here field cooled and near field cooled nicely.
Professor Lee, can I ask a question?
So when people saw this one from Spanish proposals, and they thought, oh, these are spin glass. Yeah. But then ultramination measured space heat and found the quadratic behavior. So this y-axis is C over T, x-axis is temperature. So this linear behavior means quadratic behavior of space heat at very below TF. And another thing is this is a piece of concentration. So unfortunately, in this system, chromium, magnetic chromium and non-magnetic gallium, they have this mixing, intrinsic mixing problem. So no matter how hard you try to make this pure sample, always the best concentration we get of this magnetic ions is 98%. So 98% of these magnetic lattice are filled by magnetic ions, and 2% are occupied by gallium, non-magnetic gallium. So intrinsic non-magnetic doping. But still, you can see here when 92% is occupied by magnetic ions, and this T-square behavior is only up to like 2.5. On the other hand, 98%. Yeah, then you can see this T-square behavior is all the way up to like 4 Kelvin. Yeah, so we can see from here, even from here, we can say that T-square behavior is intrinsic to these systems. And this was very surprising because if it's ordinary spin glass, then below freezing temperature, space heat goes linearly with temperature, not the quadratic. So that was surprising. But then I did experiment, neutron scattering experiment with Colin Brohol and Gary Eppley when I was a student. And we convert the neutron scattering intensity into imaginary partial dynamics of stability. And we plot that as a function of energy. Then you can see the above TF, the 20 Kelvin, is a gradual increase, right? So when you start decreasing temperature down to just above TF, let's say 5.1, then this spectral rate is shifted down to a low temperature. That's understandable, because the relaxation becomes slow and slow. On the other hand, further cooling from TF to 70 millikelvin, you can see spectral rate at the low energy got depleted, and this form, chi delta omega, becomes linear up to kBTF, kBT times TF. And this was also surprising because if you do a similar measurements on ordinary spin glass, and from above TF to close to TF, this is the same behavior. The session will show the same behavior. But even further cooling, ordinary spin glass will remain flat. Yeah. So this linear behavior in chi delta omega at low energies in the frozen state was also surprising, but in fact, yeah. But this, I think this is a glassy state. So in fact, this is consistent with the space heat, quadratic space heat, and the chi delta omega and the linear dependence. They are consistent because it is nothing but the density state is omega to the d minus 1. So it is a two-dimensional, so that explains. And then space heat is a t to the dimensionality.
So just to understand it again. So you see, for an ordinary spin glass, the energy dependence of the susceptibility would just flatten up to some
stay there. Yeah,
at low temperatures.
That's right.
And what you see here is that it goes down again, which means that you don't have what? It means that you don't have excitations at these small energies.
Right. Yeah. Some it has some. It's like a Boltzmann. It's like a well-defined spin wave time excitation.
Yeah. And question about these susceptibility measurements, these temperature measurements, are they depending on the cooling rates?
Oh, that's what I'm going to tell you. Oh. Memory effect. Very good. So yeah. Okay. So I will say that there are two different kinds of glassy, magnetic glassy state. One is a spin glass and one is spin jam. So without worrying about microscopic origin, let's assume that the spin glass, canonical spin glass, has this rounded funnel type energy landscape. On the other hand, the glassy state of fluctuating magnet that we call spin jam has this kind of non-hierarchical energy landscape. Let's just assume and see whether this hypothesis works for explaining experimental data. So how can you prove these two different energy landscapes? And in fact, experimentally, we can do that by measuring this so-called aging and memory effect. So this is related to Sergei's questions directly. So now this is a temperature and scaled by TF, and this is a bulk flexibility. So as I told you, usually when people perform these measurements, what we do is from high temperature above TF, we cool the system down and zero field. But let's focus on zero field. And then base temperature, we crank it up a little bit, and then we matching up while taking the data. Now, instead of that, let's cool the system from above TF, below go through TF, but instead of going all the way down to base temperature, let's just stop in the middle of the way. Yeah. So between some temperature between TF and the base temperature, and just stay there. Just stay there, doing nothing. So let's say, and for waiting time, certain time, and then cool down to base temperature, crank it up a little bit, and then do the usual measurements. Yeah. So let's say this black line is when we didn't stop all the way down and do nice straight line. Yeah, and then we have this cursor. Now, when we wait at this temperature a little bit and then longer and longer and longer, the spin jam case, the system that we call it spin jam case, it starts showing this, going down, signal goes down. Yeah. So okay, let's consider even we waited like almost 5 days, 100 hours. So when we wait here and then cool down and start coming up and measuring, somehow, so while waiting, what happens is while waiting, the system goes relax into a low energy state slowly, right? And so in deeper, lower, even lower energies, the longer we wait, the lower energy the system will go down to. And somehow when we cool down base temperature and crank it up, and somehow the system remembers where they were while waiting. Yeah. So that's why we call it memory effect. And also waiting and goes into a lower energy state is aging. That's why it's an aging and memory effect. Somehow it remembers where they were. Yeah. Now we do exactly the same measurements on a canonical spin glass. This is now the non-magnetic copper and 2% magnetic manganese atoms. And then when you do the exactly same thing, this color coded, for instance, this violet is only waited 6 minutes. And 1 hour, gray is 1 hour, and brown is 3 hours, and so on. And the red one is like 105 days. You can see here, spin jam case, even 5 day waiting, over 5 day waiting, it never develops deep. It's just like a smooth shoulder here, right? That's one thing. But the spin glass case, the deep start appearing brown, the 3 hour, just 3 hour waiting. Another one is this aging, amount of aging. So the spin glass case aging faster than spin jam, right?
now can we? So how much it aged? We plot as a function of waiting time. Then this spin jam case is slowly age. And the other is spin glass and quickly age. So there are two things: quick aging, age faster in spin glass, and spin jam just slow age. Another one is the deep appeals in the spin glass, but only shoulder appeals in spin jam. So how can we? So this may be experimental evidence for two different energy landscape. I'll just skip this one. We do similar things in a different waiting temperature. So my student and Jiawei did a Monte Carlo simulation. I don't know the details, but they did. So if you're interested in, you can. I think this is written in the supplementary information. And they follow this Monte Carlo scheme published in this paper. But they had to modify. And I think their scheme was not enough. That much I know. And so they have to modify, and that modification was this channel, my student channel inside. So what they did was Tianran and Jiawei, they did some Monte Carlo simulation on these two different energy landscapes. So they reproduced. So if the energy landscape is non-hierarchical, almost flat, then they produce this shoulder-like memory, while energy landscape is rather funnel type, then the deep-like memory was reproduced very quickly.
Is this difference quantitative or qualitative? I mean, in other words, the derivative in the spin jam is never negative. I mean, to have a deep, you need to have a moment.
Oh yeah. I mean, so these are the different waiting temperature. Right. So around here, it's never goes into a deep. A good question.
Why should I have a memory at all for the spin jam case? Because to me it looks just flat, right? That's what you say. So
it's not flat. You say
Well, there are fluctuations, yes.
Right.
So that's it.
That's what.
So, but it looks like what you seem to tell us is it doesn't matter whether they're here or there. It's all the same thing.
No. In fact,
while in your glass case, it probably depends whether I get trapped in the more excited metastable configuration or somewhere down there.
No, I mean even here is not like all metastable states have exactly the same energy. They are very different. I'll show you.
So it's a mix kind of. It's like you could say many spin glasses coupled together. So to say. I mean, this one also is I mean, I think it's a matter of degrees, right? So here, you start from here, you just flatten out, then you get this kind. So I mean, from here to here, if we can tune some parameters, you'll be crossover instead of some transitions.
Question I think related to the previous slide.
This one?
No, one before. Yeah, this one. But this curve was made when the system goes down or up?
I'm sorry?
These curves obtained
going up.
The system goes down itself.
Oh, so first we cool down, and then measurements are taken while warming up. Yeah.
Because there are people asking questions, but yes, we can hear that.
Yeah, you can stop me. Whenever some people ask questions. So then also they did this as a function of waiting time. And they also their Monte Carlo simulation, we produced this slow aging for spin jam and fast aging in a spin glass case. And in fact, this plus symbols are the calculations, but then when we scale the same way, then simulation result reproduce the experimental data. Okay, right? So back to hypothesis. Our hypothesis about this energy landscape seems to work in explaining experimental data here. So let's move on to what kind of microscopic mechanism can produce this kind of non-hierarchical energy landscape here. All right. So now back to let me tell you a few classical spin liquid candidates here. In two-dimensional case, the carbon lattice, and three-dimensional case of pyrochlore, and quadratic two-dimensional is this is a bipyramid case. So then one can ask why this is unique in something. Why this quadratic two-dimensional SCGO lattice exhibit more prominent glassy phenomena at low temperature than this two-dimensional carbon and three-dimensional pyrochlore. The reason is the following. Reason is, now if you consider two-dimensional carbon, the Heisenberg spins, then the system has local generalism at the mean field level. We can rotate, I didn't show this one, we can rotate the 6 spins along these hexagons collectively. It's called the weather-vane mode. And at the mean field level, such excitations will not affect the other spins at all. So that while performing that weather-vane mode, the system will remain in the classical ground state manifold. Same thing for pyrochlore, the Heisenberg spin case. It has the hexagon, we call it hexagon mode. So in this case, is the 120-degree rotated spins, but this one is a collinear, up and down, plus minus, 6 spins. They can rotate freely at the mean field level. On the other hand, this SCGO case, can see, I don't know, you saw this. So the one set of classical ground state is when, so this is a top view of this lattice. The red lines are the one carbon lattice. Blue lines is the another carbon lattice below. And the center of this, the 2 triangles, triangle is the this triangular lattice here. And the classical ground state is when every tetrahedra has 0 net moment here. So you can see the one red triangle at the center, they form one tetrahedron. You can see the plus minus, so they cancel each other, the two pairs of antiparametric spins. And the blue triangle in the center, again, you have plus minus, total spin 0. So every tetrahedron is 0. So, but one bipyramid, the 7 spins forming one bipyramid are collinear. Yeah. And then you go here, and then you switch one 120 degree and another 120 and so on. So if this is a classical ground state, but now you can see this system also can have at mean field level 0 energy mode, but it is not local. It is extent is a partial. So only partial number of spins are involved. But in this case, let's say this, we can rotate this 3, then the remaining spins, they don't care. And then if you go next, you have to rotate this together, this together, and so on. Yeah. So you have to rotate as long as we want to stay in the classical ground state manifold. We have to rotate all the spins along here and go here, along here. So the straight line, almost straight line in this particular case. And if we can have slightly different configurations, then we have to rotate along curved lines as well. I call it spaghetti mode, straight spaghetti or curved spaghetti mode. But so difference between these two fluctuating lines and this SCGO is the zero energy, classical zero energy mode is non-local in this case. And that's why freezing becomes more prominent than the other systems.
So these non-local spaghetti modes, as you call them, they are really 1D structures, or
it can be also connected.
Well, yes, it can, but it could be.
Basically,
the minimum thing is some kind of 1D.
That's right. That's right. That's right.
You cannot stop, so you
cannot. You have to go from one end to the other end, all the way. That's why that's why it's entropy. In fact, if you count the entropies, then it's an entropy. So I mean, I'll just tell you this. So if you count if you estimate entropy of the classical ground state for this 2D carbamide and 3D pyrochlore, and as a function of the size of the sample, then the entropy grows with the volume, right? Because of this local zero energy mode. On the other hand, SCGO case, no, the entropy in fact grows with the perimeter of the volume, the perimeter of this area, because of extended local zero energy mode. So that's what Isaac Clich he counted the entropy. Okay, the question, in fact, as some may ask, is okay, this transition is intrinsic or extrinsic, because we have this non-magnetic mixing problem, and there were two camps back in 1990s, but this Philip Mendel, the NMR guy, he did very careful measurements, and conclusion was, in fact, this spin glass like freezing, in fact, is intrinsic, not extrinsic. But that, I think, is consistent with Arthur Ramirez's his data also. Okay, now microscopic origin of this complex energy landscape. So when we say classical spin liquid in this kind of material, in fact, we are only considering this zeroth order, the spin Hamiltonian. So if you only consider zeroth order, mean field level, and then plot the energy landscape as a function of some kind of spin configurations, then we'll have this flat energy landscape made of collinear, coplanar, non-coplanar bipyramid states. As long as each tetrahedron has zero moment, total zero moment, right? On the other hand, we have to consider this quadratic term, let's say. If you consider quadratic term, next order term, then this flat term, the degeneracy will get lifted, of course. And so we'll have this, so then we have this roughness in the landscape. We'll have global ground state, of course. Yeah. And this is basically root 3 by root 3 structure of the triangular polaris, in fact. But then we have this metastable state that is collinear state. But from one collinear, each bipyramid collinear state, or another one metastable state to another metastable and the global states, then we have this potential energy barrier. Even though all these states are classically mean field level ground state, but now they are not anymore, right? But see here, the number with metastable state, as I mentioned before, is a grow exponentially, with perimeter. So we have this massive entropy, massive number of macroscopic number of metastable states. And I think the 36 number of global ground state. So when we cool the system down, the system will go to this metastable state, which has a short range correlations, not the long range correlations. only the global ground state has a long range order state. And having this global ground state doesn't mean anything because number of metastable states just dominates completely entropically, right? And of course, if you wait until universe disappear or whatever, then yeah, I mean the system will go down to global ground state. But what's the point? So in fact, this is called order by fluctuation or order by disorder. And this one, order by fluctuations phenomena was theoretically studied by many people. Yeah, which in fact, I didn't list. I don't think I listed everybody here, but Delane, Chris Hanley, and then such as Chukov and everybody, Young Becky, and so on. But our approach was different in the sense that they focus on what is a ground state, global ground state. On the other hand, our work focused on energy landscape, characteristics of energy landscape, and counted entropy of the local minima and energy barrier as well. So there are, in fact, if you let me summarize this. This phase diagram, this SCGO is the following, and I think it applies to a lot of all the spin jam states. So there are two energy scales. One is device temperature, yes, by the J term. Another one is another much smaller energy barrier, yeah, produced by the quantum fluctuations. So when you cool the system down from high temperature, from the thermal paramagnet below device temperatures, you'll be at we call either corporate paramagnet or classical spin liquid. But then if you cool down enough, then the system will freeze, and we call it spin jam. And low energy excitation in this spin liquid state and low energy excitation in spin jam are different. And right. So now, how about this behavior in this frozen state below TF? And this stress heat and dynamic sensibility. In fact, this can be explained by Halperin-Saslow mode. So even though the system does not have a long range order, the low energy excitation can is dominated by Goldstone-like mode, collective mode, and that will give us stress heat of T to the dimensionality and then kind of omega to D minus 1. And that explains our data qualitatively. Power exponent can be reproduced, but coefficient, in fact, Sergey, I'm sorry, Alexei told me that his name is Choker. Yes, Choker in Britain. He published one paper last year and saying that this Halperin-Saslow mode should be modified to explain the glassy state of fluctuating magnet. So we call it spin jam, but I hope people start using the term spin jam, but the community hasn't picked up yet. All right, now let's move on. So far we studied the spin 3/2, called semi-classical, but let's consider another one. They're slightly different. So this is in this compound, marine iron is kappa 2+, and you have this one spin, one unpaired electrons, and spin half. They form marine ions form scalars, nice scalars, and they are decoupled. It's a nice two-dimensional. So, all right. Now, if we have a tellurium, pure tellurium, then because of quantum okay, here. The interaction between kappa ions has to go through, because it's EG electron and it's surrounded by 6 oxygen. So quantum chemistry, it goes through oxygen and go to tellurium, or the tungsten, depends on what atom you have, and on another oxygen and then copper. There's a super exchange path. And these are sort of almost 90 degree. These are J1, and 180 degree will be J2, second nearest neighbor interactions. And so since it's a super exchange going through tellurium or tungsten, and this J term will depends on wave function of tellurium and tungsten, right? Yeah. And so if we have a tellurium case, it turned out J1 is strong, dominant, still under ferromagnetic. If it's tungsten, then the J2 is dominant, still under ferromagnetic. Okay. So, but then
why can't I? Why is it quasi two-dimensional?
Because there's no mixing. So if you go here, then you can have, you go here and you can go here and here, but when they do go through here. When they do ab initio calculations, this coupling is very, very small.
Okay, it's just small.
Yeah, just small.
Zero, but just small.
Yeah, negligible. I'll show you this experimental estimation as well. Negligible. All right. So when we have tellurium, 100% tellurium, then J1 is very strong. Then you have this nice narrow state, experimentally as well, and theoretically is also improved. If we have a tungsten, then J2 is strong antiferromagnetic. That's why we have this stripe order. Yeah, fine. But now, if we mix tellurium and tungsten, then this the long-range order at two endpoints quickly disappears, and then that this order will get maximized when x equal 0.5, the 50% mixing here. And theoretically, I think is one of these papers. And theoretically, they say a copper tellurium case belongs here, and the tungsten case belongs here. And 50% case is somewhere here, and then the mean field calculations, they say, well, you shouldn't model. And that, shouldn't model. So these are experimental data for two endpoints, tellurium and tungsten. And one thing I want you to remember is, of course, as long as you have this long-range order, if you measure the Magnum spectrum, you have this very nice collective Magnum spectrum. Okay, and same thing for tungsten case. All right, good. Now, when x equal 0.5, 50-50 mixing case, muon spin USL, they didn't find any signature of long-range order, the ordering down to 17 millikelvin. And it says Nature Com paper, and they claim, oh, these are spin liquid, quantum spin liquid. But now, when this PRB Watanabe et al., they measure this heat, but then they have this anomaly here around 1.4 Kelvin, about between 1 and 2 Kelvin, and below which stress heat behaves quadratically. Similar to Harper and Sasso mode as well. And then when people do neutron scattering measurements, I think this is Kato-Kuri. And so the two endpoints, you have this Magnum dispersion here. And here also, if you look closely, I'll show you my group's data is much better. So you have this similar Magnum type dispersion with the dispersion excitations here. But it's a broad in energy, the diffuse, a little bit diffuse than the two endpoints. So, but you can see here, if you look at the space heat and neutron inelastic neutron scattering, you can see, oh, this is spin wave light. But then if you look at the USL, no, there's no ordering. So there's a controversy there. That's why we did neutron. They jumped in this field and tried to figure out why this seemingly contradicting experimental data. So what we did was we chose very low energy. So we set up the experiment so that we can probe very, very, very extremely low energies. And we have to go down very low temperature, so we use the dilution fridge. So this is a neutron scattering data. So this is a 0.1 millivolt all the way up to 20 millivolt and so on. And you have this very nice dispersion, yeah, the phonon, sort of phonon spectrums, right? Well correlated. And then if you look at now here is a constant energy cut as a function of Q, and high energies we have this this is powder, so powder average is upper peak, but very low energies you can see this asymmetric. So when you see these asymmetric features in a powder sample, then we immediately know that the magnetic injections are low dimensional because it's due to powder averaging. I'm not going to detail, but anyway, now we focused on very, very low energies here as a function of temperature. So you can see here from 7 Kelvin is a nice streak. Yeah, it's like a magma light. Then cool down to 1.7. Then you can see very low energy spectral weight increases, becomes brighter and brighter. Because the spectral weight shifts it to low energy. That's if you remember for the case of SCGO. But then again, below 1.7 all the way down to 0.25 Kelvin, this low energy spectral weight got depleted. Like SCGO, yeah, it's a deja vu of SCGO. So, so then, oh yeah, immediately when I see this kind of data, immediately there must be spin freedom because spectral weight, in fact, goes into elastic channel. Yeah, that's why you get depleted. So, and then we integrate. We did this kind of measurements at many temperatures and spanning TF, and then we integrate this spectral weight around here and then plot this as a function of temperatures. Then you can see here from 12 Kelvin goes up, and then around 2 Kelvin goes down. So these are inelastic. So this spectral weight got decreased, goes into elastic channel. So there's a spin freedom. And also this elastic, you have this nice asymmetric, and we can fit this one to the two-dimensional correlation function, and we can extract the in-plane correlation length, which is the second Nielsen interaction distance. So J2 is strong, that also. And then also we plot the kind of omega as a function of omega, and then base temperature, in fact, is linear up to 0.1 millivolt, which corresponds to 10 Kelvin. Also 1 Kelvin, so it's close to a TM. So all makes sense. So somehow, even though it's two-dimensional random J1 and J2, but physics is the same as SCGO, spin jam, right? So in this case, Curie temperature is 71 Kelvin. Above Curie temperature is a thermal paramagnet, and below Curie temperature is a spin liquid. And stress heat, you remember, is a linear in T. And so another thing is I didn't explain. Here, the above TF, we fit the data to arctangent. Because arctangent means if the system has, instead of one characteristic relaxation time, if you have a distribution of relaxation time, different relaxation time, then you have to add. So for each characteristic relaxation time, you will have one Lorentzian, right? And then if you integrate with some the Lorentzian with different relaxation time, then you get arctangent. And if you assume that there is a low limit of the relaxation time, then you get this gamma mean, and you can plot the gamma mean as a function of temperature and so on. But anyway, so above TF, we have this arctangent behavior of height alpha omega, then it's relation to time at very low energy we define as a distribution. On the other hand, this below TF goes back to one particular relationship of time. Yeah. So okay, so this seems to be consistent with the Hamiltonian theory, though. But if you look at the more details, in fact, now I'm more encouraged by Choko's paper that I didn't read, but you can see here the power law, this exponent can be explained by Hamiltonian theory. On the other hand, if you look at the coefficient, this is a Hamiltonian theory coefficient, in fact. I cannot tell you this calculation is correct. This is what my student did. He did many times because I couldn't believe. So I asked him to do many times. So he took this experimental values for these constants, chi naught, and spin stiffness and so on for the three different systems. One is a spin half, J1, J2. Another one is a spin 1, triangular lattice. Another is spin 3 half, this bipyramid systems. And we got this experimental values and put into this formula. And so the coefficient of space heat can be determined by experimental values and compared to calculations. Then they are off significantly, not just like a factor 2 or 3, they are off like several orders of magnitude. But I don't know if this is correct, because here chi naught is in the unit of EMU, but EMU is very tricky. But this is what he could do best as of now. So if we trust this, then you can see coefficient cannot be reproduced by Hamiltonian model. It has to be modified. That's what we've been trying to say. In fact, according to Alexei, Choko is trying to say the same thing, which is good. So let me just summarize. Instead of global ground state, the energy landscape is important concept in understanding low temperature property of this glassy magnet. Also, glassy magnet should be further categorized into two groups. One is ordinary spin glass, another one is non-ordinary spin glass. We call it spin jam, but I hope the community will pick up that term, spin jam. And then again, this energy landscape, in fact, can be probed experimentally and theoretically as well. And last one is Hamiltonian mode theory. Theory should be modified, and in fact, that's why I'm here, and that's why Alexei invited me. I hope Alexei and I can collaborate to modify Hamiltonian theory. Thanks for your attention.
Let me just ask you a question.
Sure, yeah.
Can you remind again, so what were the main assumptions of this Hamiltonian theory?
Oh, Hamiltonian theory, yeah. So in fact, the main assumption, in fact, I think probably Alexei can explain better than I think. So how it says, yeah, this is back in 1970 when ordinary spin glass was a very hot topic. So he considered two excitation scenario. One is two-level scheme, and another one is this Golson mode line. So as long as there is some finite spin stiffness, then even though the system does not have ordering, still the low energy excitation will be governed by this finite stiffness. And that is basically Golson mode. Am I right, Alexei?
As much I'm yet to master it, but yeah, I think the query is basically there.
And you're promising to tell why this coupling to the third dimension is so ridiculously small that one can neglect it.
Oh yeah.
Can you maybe show that again?
Right. I think that for instance, so when I do this, so this is we fit the data this SOQ. We only so if it's three-dimensional, this will be isotropic, and so we also estimated this outer plane correlations is basically zero. So that's one thing. Another one is people did a linear spin wave, sort of. I can show you. In fact, I can show you one here. My series colleague at UVA, in fact, he sent me this today. So he has been doing this Monte Carlo simulation, and yeah, here. So this paper, other paper, in fact, last year came out. I think European group. They studied by doing ab initio calculations for every possible J's. They considered up to 5 J's, and they introduced a random, this mixing randomly, and they construct this random J's. Not this. So this is different from J1, J2 model. Yeah, and once they construct this, they did spin wave calculations, simple spin wave calculations. They found this. So this is experimental data. This is the calculation. There's a free software package that calculates the spin wave. And so they found this nice Maudon-like case even for x equal to 5, and that in fact qualitatively explain the Newton data. They say. So the question is, in fact, a slightly different question. In fact, the question is, even though spins remain random in this case, and we know that now our work, in fact, show that only 10% is frozen, 90% is still fluctuating. So even though the spins remain more or less, well, mostly random, why this is a good dispersion, right? And that's the thing, and Jawi this Monte Carlo simulations. He considered only 2D. So ordering temperature. I think this related to your question for spin glass. So since he considered only 2D, then ordering temperature, there's no ordering at finite temperature, right? So, but you could see this sort of order parameter. Yeah. So he considered this Edward Anderson order parameter, and so but he did something more than the PRL paper. So he did I don't know the details, but he did the Monte Carlo simulation going to Lambda Lipschitz equations, and then he constructed the space-time Fourier. So he constructed the dynamic structure factors. This is not this result, and I show you. And his result is the following. So when the tungsten, no, this is a tellurium. This is tungsten. When tellurium is 90% and tungsten is 10% only, then you can add this endpoint is pi, half. This is a Q. So you can see here the spectrum, the intensity in fact is strong around the pi. The similar is tellurium, 100%. Now you go, so now you increase the tungsten ratio, then now it's a pretty broad, right? This is a pi, and this is a half 0, it's a tungsten. Yeah, this is not the powder averaging. This is a single crystal along high symmetry directions. Now it's a 0.5 case. I like this, but so now it's from here, pi, yeah, to pi 0. He shifted. And he could reproduce this nice, now this is John center. Now if you look at the John center, usually it's a John boundary, since it's anti-ferromagnetic, John boundary very strong, and John goes to John center is weak. But he could reproduce very nice dispersion of magnons. It's very surprising because frozen moment is such small. I don't think he calculated how much spin will be frozen. But another thing is I saw, I had a Zoom meeting on this morning. And so in fact, if you look at here, it's a very weak signal here. So if you remember spin chain, right? The spin chain, the spin half spin chain, if the classical, then you have this nice one magnon mode. But if you have a quantum, then instead of this nice magnon mode, classical mode, is a lower bound of magnetic excitations. Then you have this upper bound for a if you have a ferromagnetic upper bound, and in between you have this fractional bosonic excitations, right? Is a fraction, this continuum, right? Purely due to quantum fluctuations. So I asked him, look here closely. You see instead of, in addition to this nice simple, the magnon mode, well-defined magnon mode, is there any scattering in the continuous spectrum? The scattering, maybe it might be different from the spin half chain, but so if it's spin half chain, then it will be something like this, and then you'll have this, and you'll be filled up. But if you look at closely here, you have this extended here. So he'll look into that.
Another maybe more general question is,
yeah.
So you try to split, to differentiate between glasses and gems.
Yeah.
If I remember correctly, there are other glasses, glass transitions, which are considered maybe not spin for spin, but for other systems. And there's something called fragile and strong glasses. Fragile glasses and strong glasses, structural glasses.
Structural glasses, yes.
Right. So is there any connection between?
Very good. Yeah. That's why we use the jam. I mean, when we said, oh, jam, but then we realized that the jamming physics, in fact, is hot in that field, right? Jamming. So, but then so we try to, in fact, connect to that physics. And we found, I cannot tell you exactly, but we found that their jamming is slightly different from the jamming.
So what would you call their jamming in this? Is that the fragile glass formers, which are more the jams, or as opposed to the strong glasses, or what? Because what I just remember is that there are the strong glasses and fragile glasses. And,
right. But in fact, that much I don't know. Yeah. So that's a good point. In fact, I want to know more.
Perhaps a naive question. I don't know. I mean, one of the hallmark of spin glasses is you have a model. You have a replica symmetry breaking.
Right.
Yeah. Jam. What? I mean, from the replica symmetry breaking perspective, what differentiates a glass from a spin glass?
Sorry, I cannot answer you because I'm not very familiar with. Maybe Alex. Maybe.
Well, I think this connects to the question by Sergey. I was also thinking process comparing to like mostly in terms of the replicas.
I see.
Replicas. Precisely when the landscape has a lot of fine structure.
Right.
I was also curious whether jam can be attributed to this one step, which I think might be a lot closer to this. Like a lot of local minima that are not organized. Books that themselves.
So you think that the spin glass model is more like a gem?
Perhaps because that's also what's the window glasses are out there. Those are spin.
I see.
Mhm.
I think all the models I could think of when people try this perspective magnets, they're all global purpose.
Oh. Mhm. Yeah, one can connect this physics and the structural glass will be great.
The other reason why this is might be appealing in this case, because what you would see there precisely is a cool down. You see a transition, but actually what happens is the system gets up at a state.
Right.
It actually goes much longer temperature to actually.
So let's say, using this terminology, let's say Kilpatrick will be a standard spin glass, while big spin glass will be a gel. Okay. Your bet. Let's say you guess in that way.
Yes.
Okay.
Maybe there are questions. I know they're saying I should speak louder because they cannot speak.
I see.
That's the trouble of the hybrid seminars. I mean, I cannot turn off the sound because then we get the.
If they send any questions, we can send questions. People can send questions by whatever.
By chat.
By chat. See that? I saw tons of chat things in there by the year, 11 chats.
But they are just
complaining
about
how we speak.
But they are just complaining.
I see. Complaining what Tilly is saying, please ask questions, or there was actually one question.
Yes, can you hear me? I'm afraid you cannot hear me. Hello? Yeah.
Yes.
You should just put your mic. Good seminar rooms. Because they do construction to make it even better.
Oh, I see.
I hope
So we have this hybrid system in the seminar room, but then they are upgrading it. And so I guess since we scheduled your seminar on a pretty short note,
Right.
there was a conflict.
Right.
it sounds like the
Yeah, I think we should discuss technical.
Right.
Okay.
Yeah. Thanks.
Thank you.